this is the spec for the first module on limits. We could call it limits 1, assuming that in the future we'll do more advanced modules. But this is really just to make sure students understand the basic idea of limits, or maybe if they don't, to actually teach it to them. So we're just going to give them a variety of functions. We can maybe have, I don't know, 5 or 6 different types of functions, but then of course we will pick random numbers in it to shift it around or change it so they don't look exactly the same. So a neat kind of basic one would be something like find, or we could write the limit as, and we could change up the variable. We could say x, we could say a, we could say whatever we want. The limit as x approaches, and here we could pick some random number. Let's say the limit as x approaches 2 of, and then let's do something interesting here. So let's say we have 3x squared times x minus 2 over x minus 2 is equal to question mark. And if you want, we could write it this way. We could multiply the top out. So it's 3x to the third minus 6x squared. And students would have to figure out that they have to cancel it out. Or maybe they don't even have to figure that out, because here we want to encourage people to have an intuition of what limits are. That what happens is we get closer and closer to the point x equals 2. So the first time that they click hint, and it's up to you whether you want to graph it or not. I think since this is the first one, it wouldn't hurt to graph it. So this thing's going to look something like this if we were to graph it. 3x squared is going to be a very steep graph. It's going to look something like that. But at x equals 2, it's actually going to be at 12. So this is, this right here is 12. It's going to have a hole there. And you want to be careful that you actually have room to graph it on the paper, to actually graph the hole. It's going to be undefined. But it's up to you. Sometimes you might want to graph, sometimes not. Or you could just graph it every time, or maybe you graph it as one of the hints. But regardless of whether there is a graph, the first hint is let's write it this way. Let's see what happens. Let's see what happens as we approach x equals 2 from the left. We can actually give the students a table where you have x, and then you have f of x, where you have the function f of x. And we could, or you could write, you'd want to write f of x. So let's say, so we're approaching it from the left. So at first you could do x equals 1.9, then you could do 1.99. And you could do 1.999, and then you would put the appropriate numbers here. I don't have my calculator out, but you would take 1.9, put it here, so it's 3 times 1.9 squared, whatever that's going to be. It's going to be some number less than 12. It's going to be even closer to 12, and even closer to 12. And so it says it looks like it's approaching 12. It looks like it is approaching 12. And if we do draw the graph, we could show that we're approaching it from the left. We could show that we're approaching 2 from the left, and we could show that the numbers look like they're approaching 12. So we could say looks like the numbers are approaching 12. Then if they click hint again, we'll do the same exact thing, but we'll approach from the right. When we approach x equals 2 from the right, we get, and then we do the same thing. We have x, and then we have f of x. We're approaching from the right, so we could do 2.1, and then you could do 2.01, and you could do 2.001, and so on and so forth. We're going to get numbers that are slightly left of 12. So once again, let's say, hey, it looks like we're approaching 12. Looks like we are approaching 12. And then finally, if they click hint again, we could say, hey, so the limit as x approaches 2 of this f of x is equal to 12. And so you could, and you could show people that, look, this cancels out for all other values. But I really want to make people have the intuitive sense that a limit is just what's happening to the function as we get closer and closer and closer to this value. And in all of the cases, you obviously want the correct answer. You want undefined always, because the limit may or may not be undefined. And then you want just some other numbers that might trip students up. Now, the other interesting functions that we might want to experiment with, the other interesting functions, let me clear all of this. The other interesting functions, you would want to do things like the limit as x approaches, you pick some number. The limit as x approaches 4 of the absolute value of x minus 4 over x minus 4. And so this is a case, and you want to give the appropriate hints. But you could, if the first hint is for x is less than 4, or even you want to do the same thing. As that's probably the simplest brute force way with kind of a calculator. As we approach x from the left, and then just do 3.9, 3.99, 3.999, see what values you get. Then as you approach x from the right, you do 4.1, 4.01, so forth and so on. See what values you get. And you're going to see they're approaching different limits. As you approach from numbers less than 4, you're going to get a negative 1. As you approach from values greater than 4, you get a positive 1. And actually, so the number isn't, well, it's going to be undefined here, but we might even, you could put coefficients out here. But in general, it's always going to be undefined. If you were to graph this function, which would be kind of a neat thing to do, especially if you were to graph this version, 3 times x minus 4 over x minus 4, it will look something like this. So at 4, 1, 2, 3, 4, it's going to be below 4, you're going to be like this. You're going to be at negative 3. I'm doing the version with the 3 coefficient out here, and obviously this is going to be question mark. 3 coefficient out here. You are undefined at 4, and then you take up there, and it's going to be something like this. And so what you're going to find, the first hint is going to say when you approach x equals 4 from the left, you're going to get the function is at negative 3. When you approach x equals 4 from the right, you're going to be getting that the function is positive 3, and you're going to say that the limit does not exist. Or maybe instead of undefined, does not exist. Does not exist. Now, the other types of functions we might want to do are functions of the sort. So we could define f of x as being equal to, really basic functions. So it could be x. It could be x if x does not equal 2. And then it could be equal to 3 if x is equal to 2. And obviously, when you take a limit on this, what's non-intuitive is at the x, this is one of those functions that just have a discontinuity point. Or let's see, this function would look like this. So it would look just like x. And you could put a coefficient out here if you want to change it. And obviously, all of these things could be random numbers. All of those could be random numbers. But it's going to look just like this. The function is going to look like this, except it's going to have a hole at x is equal to 2, where you would expect it to be equal to 2. It'll just continue on. And the function will be equal to 3 there. And these type of limits will be useful because they'll see that the limit, so they'll see that the limit as f x as x approaches 2, well, that's the question we would write in this circumstance. They're going to see that the limit is different than the value of the function. If you take f of 2, you get 3. If you take the limit, you're going to get 2. So once again, another interesting one. Try it out with different numbers. And I encourage you to think of other things with holes, things without holes. And actually, probably 1 out of every 4 problems, you should just do a really simple, straight up, limit as x approaches, some number, as x approaches 1 of just a number where you just really just evaluate the function. So it could be 3x squared minus 2, or anything like that, where you literally just put it in the function and you get a value. But you want to try out the values below 1 and above 1 and show that it's really approaching that value. You really get the sense of the difference between the limit and just evaluating the function, which especially an example like this gives you.